Hey Level 3, so this is your FAO for Redox tutorial 1 part B on electrolytic cells. It cut me off before and I didn't quite get to finish this. So when we do the cell potential, it's reduction, which was our water, minus oxidation, which is 1.06, and that gives us negative 1.89 volts. It's negative, which means non-spontaneous. Now what I'm doing here is I'm not actually giving you how to answer the questions for your internal. I'm just running through the principles by which this works. So this is a tutorial so you understand what happens in electrolytic cells. We're going to do one more example of aqueous. So we're going to do aqueous copper sulfate now. Okay, so hopefully you see the sulfate and alarm bells go. Okay, if you have sulfate, it means that the anions can't go to the anode and instead water is going to get oxidized. So again, we can draw a template cell and you get really good at these. Okay, electrons flow from the anode to the cathode where reduction occurs. This is made out of platinum or carbon. This is the anode where oxidation occurs, made out of platinum or graphite. Anions are attracted to the anode. Anions are negative, therefore the anode is positive. Cathode will be negative. Okay, there's our template. So we haven't even put in our details for this cell. So we're going to put CuSO4 aqueous here. And we know straight away, because we see the sulfate, that the oxidation equation is going to be water, which is always a liquid, to oxygen, okay, gas. So we can balance this half equation. So we need to add a second water, okay, and then we add 4H plus to the right-hand side and 4 electrons. Sorry, I've done that in a really dumb place, but you guys get the gist. So then we'll do the reduction equation. I'll do it over here just to make room. Cu2 plus... Oh, sorry, before I do that, I'll explain what's going to happen here. So remember for this one, it's going to be, is it the cations or water? And we look at the reduction potential. So here's copper ions, here's water. Which one's got the higher reduction potential? Copper does, so copper's going to get reduced. So copper aqueous plus 2 electrons goes to copper solid. Okay, let's quickly go through some obs. Water is colourless and O2 gas is colourless. So at the anode, we will see bubbles of gas. Okay, oxidation, this part here, copper ions are blue and copper is pink metal. So therefore, we're actually going to see this get coated in pink metal. And the mass is going to go up. And why is the mass going to go up? Because we're reducing one ion into one metal atom, and that metal atom is sitting on the electrode, okay, and therefore in the solid state, and therefore its mass is going to go up as this reaction goes along. Let's look at oxidation numbers. So it's always one species that changes in oxidation number, and if we look here, we're forming oxygen, so oxygen's got an oxidation number of 0 here because it's an element. So then what's the oxidation number of oxygen and water? And we know it's -2. It's one of our knowns. So -2 to 0 is an increase of 2On, okay, and an increase in On equals oxidation. The other thing you must mention is that a loss of electrons is oxidation. And we'll talk all about this, we'll look at this when we do examples, and I'll mark one of your examples just to make sure you guys are all good. So the oxidation number of copper ion is +2 and it goes to 0. This is a decrease in oxidation number, okay, which means that it's getting reduced, okay, and just remember we put the charge in front, so you won't do very well if you get that wrong by level 3. So the final thing here, let's do a reduction potential. So the E0 cell is reduction minus oxidation. So the reduction was copper, 0.34, minus the oxidation, which was here, which is 0.82, and that gives you negative 0.48 volts. Because that's negative, it is non-spontaneous. Hopefully that all makes sense. So the final thing we need to talk about with electrolytic cells in this tutorial is electroplating. So electroplating is where we plate an object which needs to be conductive, so it's normally a metal, with another metal. So I'm just going to show you the setup here. whenever you have this, the object that you want to plate must be the cathode. I'm terrible at drawing. That's my spoon, okay? And it's the cathode. And what happens at the cathode is reduction. So here, the next rule is that my anode must be made out of the metal that you want to plate. So we want to plate our spoon in silver. So my anode today is going to be made out of silver. We used to have some silver electrodes at school and someone pinched them. Classic. Okay, so silver electrode here. So the anode must be made out of the metal you want to plate. And here we've got our iron spoon, which we want to be coated in metal. By the way, this is actually how they do this. It's pretty cool, really. Electrons still always flow from the anode to the cathode, and the anode is still going to be positive, and the cathode will be negative in charge. So to work out what goes in the electrolyte, it has to contain, so these are all the rules, by the way, down the left. So the object that you want to be plated must be the cathode. We've done that. That's the spoon. The anode must be made of the metal you want to plate. We've done that. It's silver. The electrolyte must contain the ions. So it must contain silver ions that we want to plate. And the reason why is oxidation and reduction happens simultaneously. So as soon as we turn on the power supply, one of these silver atoms is going to become a silver ion, but at the same time there has to be silver ions in here, because at exactly the same time a silver ion forms a silver atom here. Okay, so we need to contain silver ions. We know in chemistry that silver ions you can't have a positive ion without a negative, so we just use a spectator ion, and a really good spectator ion would be nitrate or sulfate. Okay, this is the key part though, that you understand that silver ions are present in the solution. Why again? Because oxidation and reduction happen simultaneously. So you need to have some of these ions already in solution, so as soon as the power supply turns on, these can be reduced and these get oxidized at the same time. Now just to add to that, because this is happening at exactly the same time, these reactions, the solution doesn't change in conc, that's concentration of Ag+. It stays the same the whole time. And I'll just repeat why. These reactions happen simultaneously. So as I turn on the power supply, one atom forms one silver ion. At the same time, one silver ion forms one silver atom. So it never actually changes. Perfect. So this is the setup here, and that's what happens with electroplating. So this spoon's going to get covered. Okay, so the mass of the spoon will go up. Okay, and what do you think is going to happen to the mass of this electrode? Hopefully you understand that the mass of this is going to go down, because one atom continually forms ions. And so this is going to deplete, its mass is going to get smaller, and the spoon's mass is going to go up as the silver atoms get plated on it. We don't need to worry about a reduction potential for this one, because hopefully you're seeing the oxidation equation. So oxidation in this case is Ag going to Ag plus. Okay, and the reduction is exactly the same. Ag plus, but in reverse. Plus an electron goes to Ag. So this is a bit of a funny one, okay, where it's exactly the same thing getting oxidized and reduced. And this process is called electroplating. These are the three key points you must have in your cell. Hopefully that's made sense. So that finishes up for us the first section on electrolytic cells. And you're going to practice these when we do 2 practice full questions for your internal, and so you can practice then. Hopefully that makes sense. Don't forget you can refer to all of your notes when I taught this, which has also got a ton of examples. Okay, catch you soon for tutorial 2.